I'm very happy to present some of our new work on explainable AI, in particular for transformer-based models, such as LLMs. And basically, what I was kind of very lucky to be in the field of explainable AI, like almost from the very beginning. So in 2013, when people came up with methods to understand and explain predictions of deep learning models, of other types of machine learning models, we have started also working on these methods, and many of these approaches in this first wave of explainable AI, they kind of explain the predictions of an individual sample by constructing this heat map. And you see here that it's like the prediction is pool table, and this heat map or this attribution map shows you which input pixels, which part of the image was mainly responsible for this prediction. And there are many methods around who can kind of construct these kind of explanations. And why are we interested in explaining? There are at least three motivations. So one is to analyze model, verify predictions, debug models. So we have a paper where we found some bugs in models which were used in competitions where people thought these models are very accurate because they had good performance on some test data. But apparently in this case we see that this model is classifying this image as a horse, but not because of the horse, but mainly because of a copyright tag, which for some reason correlated with the category horse. So these models kind of learned a spurious correlation and used this for prediction, and nobody realized until things became explainable, because then you could verify what's going on and what is kind of the basis for prediction. Also recently, other researchers wrote a fantastic paper where they show that with explainable AI you can get also scientific insights. You can develop new antibiotics, get like insights and hypotheses on your data, which can be helpful for progress in the sciences. And yet another reason is more like legal issues, verification, ethical issues, trust. Also, people often very much like to interact with a system which is explainable. So there could be also this dimension of why you want to explain. And when it comes to large language models, we even can be more specific. For instance, these models often hallucinate, and they are kind of more interactive. So we want to develop and adapt explanation techniques to understand hallucination, to improve these models, and to foster trust by providing sources. So for instance, if you ask like a large language model, what is the capital of Germany, and it says, okay, it's Berlin, we may want to know where this information comes from. We want the model to provide sources for the answer, and these kind of things can be potentially done with explainable AI methods. Okay, it is also very important to really be aware of what we actually explain. So do we explain individual predictions? Do we explain it in terms of attribution maps, like in the old days many people did? Or do we explain individual predictions by providing examples in the training data which explain this prediction? So there is some very interesting work on data attribution where people want to find training samples which explain, for instance, the wrong model behavior. Do we want to explain prototypical behaviors? For instance, do we want to explain like the general strategies learned by a model? We have some recent work where we kind of cluster behavior patterns and explain these behavior patterns by human understandable concepts. Or do we want to explain the model itself? So there is all this work on activation maximization, where people try to find or either construct or find inputs which maximize certain activation of a neuron, and by that, learn about what this neuron is representing. So what do we need kind of when we go towards LLMs? We definitely want to have faithful explanations. So explanations which really are kind of connected to the model and to the decision making of the model. We want in particular to compute explanations efficiently, especially for these large models. This computational efficiency is a very important factor. And we potentially want to compute kind of relevances of the input, of the context used for LLM for the individual neuron. So we want to be flexible with respect to what we want to explain. And the method which we kind of proposed almost 10 years ago is Layer-wise Relevance Propagation, LRP. And it is kind of combines all these three, or has all these three properties. It's faithful, it's computationally very efficient, it's in the order of a backward pass, and it also allows to compute explanations for latent elements of the network. So you not only have like explanations for the input, but also you know which neurons, which filters are important for the prediction. So you have the full information. And the basic idea of LRP is that it kind of redistributes the output, the prediction output. In this case, the output of this image classification task is dog. So what you do is you kind of redistribute this output layer by layer backwards through the network. And how do you do this redistribution? For that, you need to kind of first measure how much a neuron from the last lower layer, in this case, for instance, neuron J, has contributed to the activation of neuron K. So these kind of contributions are denoted as ZJK, and they are kind of the important elements for this redistribution. So we are not explaining in one step the contributions of the input to the output, but we are breaking this problem down into a series of smaller steps. So we are only explaining how much did the elements from the last lower layer contributed to the activation of the current layer. And once you have this ZJKs, you can redistribute things layer by layer and finally arrive at the input relevances. So then you know kind of how much each input contributes to the prediction. And you also know how much each element, each neuron contributes to the prediction, because you can kind of aggregate this relevance values for each element of the neural network. And a cool thing is that, or maybe first, there are like different ways to measure this contribution. So over the years, we came up with different strategies, different ways to measure these contributions of neuron J to the activation of neuron K. And these kind of strategies depend partly also on the type of layer you use. So if you have like a ReLU layer, then we have some recommendations how to do this, how to measure these contributions. If you have other types of layers, if you just have a linear layer, then we also came up with kind of formulas to do this, to measure these contributions. And basically these formulas which you have are also can be interpreted from a tailored decomposition perspective. So basically what we do is we kind of model this forward pass, or we construct a relevance model for the upper layer neuron, for neuron K. And in this case, in the case of ReLU layers or convolution layers, what you have a simple dependence. So like the relevance of neuron K depends on the activation of neuron J through this formula, which you see in the upper left part. It's just like a ReLU. It's just like a weighted ReLU. So you have like these weights Z, CK, which are almost constant. And once you have this kind of relevance model, then you can apply Taylor expansion. And we can show that depending on how you choose the root point in this Taylor expansion, so basically you choose a root point A tilde so that RK of L tilde is 0. And you have like different flexibility how you choose the root points. And depending on how you choose it, you will arrive at these different redistribution rules. And the way you choose it can depend on the properties of the layer. Okay, so this is something which we have published this paper 2017, and the method LRP has been proposed almost 10 years ago. So this is something which is really established by now. But what we were not able to do for the last years is to extend this framework to transformers. Transformer models, if you have like a multi-head attention, you have like this very nasty multiplications in the attention layers. And we are not sure how to meaningfully redistribute relevance through these attention layers. So through this softmax and multiplication connections. And this is kind of what is really key to our methods. So to LRP, it's really key that you have like a meaningful way to redistribute these relevances, because everything you get kind of depends on this. So for every new type of model, for every new type of layer, you have to first make sure that you are doing it in a meaningful way. And we, for LSTM models, we also had came up with redistribution rules. And now the question was how to do this for transformer models, transformer architectures. And very recently, we were able to propose, we call it attention LRP, so an extension of LRP for transformer architectures. It will be presented very soon at ICML, so in 2.5 weeks or so, or 3 weeks, we will present this paper in Vienna. And basically I will not go into detail here, but what we can prove is we can kind of come up with redistribution formulas and then prove that the things what we do is kind of fits the Taylor decomposition idea and can be interpreted as a particular Taylor decomposition consistent redistribution. So we're not doing this redistribution in a heuristic manner, but we always try to keep this theoretical interpretation as a kind of Taylor decomposition based explanation technique. And you can do this for this multiplication layer, and you can also do this for this normalization layers. In this case, it's just like the identity. But we have all the proofs and all the kind of details in the paper. But what is kind of really important is that with this, we are able to very efficiently redistribute relevance, very efficiently construct these explanations. So it's in the order of one backward pass, while other methods which are based on perturbations need a lot of forward operations, which are very expensive for these large language models. So some of these analyses which other methods do are very costly, and our explanations, as you see here, here is like a transformer model and a vision transformer, and the prediction is dog, and you see that attention LRP very faithfully and in a very efficient manner shows you that the relevant part of the image is a dog, while gradient-based approaches such as smooth grad, which have known to be unreliable because of this and noisy because of particular architectures and effects, especially with depth. This noisiness becomes large. The gradient shattering is kind of the key term here. These properties have been studied for some time, and especially for these very big models, the faithfulness or these methods are not very faithful. Other methods like Edman are computationally not efficient because they are based on these perturbations. And LRP, as I said before, is a model-aware method, so you can also attribute relevance for every latent element of the model. So you know, for every neuron, for every element also of the attention layer, we know in principle the contribution of this element to the prediction. And here are some faithfulness scores. So basically larger numbers are better. So the idea of this faithfulness analysis is that, I mean, this is related to this pixel flipping or perturbation-based analysis. So you assume that if your model detects that this part of the image is relevant, then perturbing this part or adding noise to this part or disturbing the pixels there should affect the prediction. So if the method says, okay, that the dog's face is the important part, which makes the image a dog image, if you occlude the dog or if you perturb these images, it should affect directly the predictions. Otherwise, this method is not faithful. If it's like a random heat map, then it will not have a large effect. And you can kind of compute these numbers and compare different explanation methods according to this faithfulness. And you see that, for example, for the vision transformer, attention LRP, like other methods like input times gradients or integrated gradients or GradCam, are not really faithful. Attention LRP and other LRP variants, which are based on the epsilon rule, are also worse than attention LRP. For the language models, we also did this comparison, and you see here that in all the models and all the data sets which we tested, attention LRP explanations were the most faithful ones. You can also see here some examples. For the vision transformer, you see that this gradient-based explanations are really very hard to interpret, and while attention LRP, at least qualitatively here, gives good results. The same is true for the text explanation. So here we ask an LLM, in what country is Normandy located? The answer is in France. And from the context, we kind of wanted to know which words in the context are important. And you see that, for instance, integrated gradient computes explanations which where kind of all types of words are kind of highlighted, but semantically these words do not have much to do with the answer and the question, while attention LRP, but also like Edman, are much more focused on words which are really related to the question. So also this is a qualitative evaluation, but you see that this kind of results correspond very well to the quantitative results which we saw here. Computational comparison. So in terms of, here we plotted this in terms of energy costs. So you can also compare the time needed or the number of queries or so. And you see that in terms of energy cost, attention LRP is orders of magnitude better than perturbation-based methods, because you just need one backward pass. You don't need hundreds forward passes to compute one explanation. Okay, so you saw that here we were mainly at the level of the input, so input relevances, input attributions. But what we also recently did is to move more towards intermediate explanation. So because sometimes this input attributions are kind of restricted, they just tell us where something is relevant, but not actually what kind of feature it is. What they do not tell us semantic information. And in our paper, which we published last year, we extended this LRP approach to concept relevance propagation, where we kind of show that it's possible to explain predictions in terms of human understandable concepts which are encoded at higher levels, higher layers of the neural net. So for instance, if you have like here a prediction B-eater, and you have this heat map, attribution map, what we wanted to do is we wanted to explain this prediction in terms of concepts which are encoded in the intermediate layer. So for instance, this one neuron here could encode the concept animal sitting on a branch. Other neurons maybe encode concepts related to colors or related to shapes, and so on. And what we kind of do is we kind of know, we exactly know how much each neuron and how much each channel contributes to the prediction. This is what we get from LRP. We get it kind of for free. And what we just need to find out is what kind of concepts are encoded by this neuron. So if we know that this guy is very important for the prediction, we ask ourselves, okay, so how can we find out what this neuron or this channel is really encoding? And there is a lot of work on the domain of activation maximization, where people try to find out what kind of, or this database activation maximization. So the idea is to find kind of samples or images which maximally activate the neuron. And the assumption is if this images maximally activate these neurons, then they encode the concepts which is encoded by the neuron. And we kind of extended this approach a bit to, instead of using activation, we also use relevances as a signal, but I will not go into detail here. But basically, this is the idea that you first, with LRP, identify what is the important channels in the neuron for this particular prediction, and then you use activation maximization or relevance maximization in order to find out what information is encoded by these channels. And we can do this also for LLMs. For instance, here we found like a neuron, for instance, number 256 in layer 18, and wanted to know like what does this neuron encode. And we did like activation maximization and found like 10 most, or in this case you have like five most, like 5 sentences which mostly activate this neuron. And you see that all these sentences kind of are focusing on transportation systems, and in particular railways. So from that you can see that this neuron has something to do with this concept railway. It kind of encodes this concept, and you can even compute like this attributions from the neuron to this sentences. And you see, for example, another neuron 2207 in layer 20, and it seems that this neuron is encoding the concept teacher. These explanations kind of show you this. So these are also like the 5 most activated sentences, or the 5 sentences which mostly activate this neuron. And you see that it's kind of really the teacher. But what is interesting is that in all these sentences, the word teacher comes in an unusual context, or like in a context where the teacher has some inappropriate behavior, right? So that either the teacher has some affair with a student, or have an inappropriate relationship with one of his students. So it seems that this neuron is not only encoding the concept teacher, but like a teacher which is behaving not appropriately. at least, yeah, this is what we can see from these sentences. And what we also try to do is to manipulate this representation. So for instance, if you have like if you prompt an LLM with this input, ice bears live in the, and it will give you the output Arctic. So we wanted to know, okay, which neurons are encoding the concept related to Arctic. So what we found is a neuron which encodes concepts like a coldness, freezing, winter, low temperature. We also found other neurons which encode concepts related to dry spells, little water, drier periods. And we found a neuron which is encoding the concept candy, sugar, sweets, and so on. And what we did now is we kind of manipulated or edited the prediction of the LLM by disabling this neuron which is encoding for coldness and activating the neuron which is encoding for dryness, or activating the neuron which is encoding for candy. And what we saw that the prediction of the LLM changes to desert and candy shop. So then it tells us, okay, ice bears live in the desert, or ice bears live in the candy store. So it's very interesting because it's still like a location. So the output is still related to some location, candy store, desert. But we can manipulate, kind of manipulate the concepts which are present in the output. And we see a lot of potential in combining explanation methods with this idea of not only like explaining the input of the model, not only explaining in terms of input attributions, but also explaining it, the inner representation, and understanding what role are particular neurons kind of playing in the prediction. And LRP is a method which allows you, or attention LRP is a method which allows you to do this in a very, very quick manner. So you can, in principle, you can study in a systematic way the representations of LLMs and be very efficient in that. So summing up, so we have a method which is able to compute faithful explanations in a computationally efficient manner. Future work we want to do is a systematic analysis of hidden representations inside transformers. We also want to go into the attention head, into the attention layers to better understand the role of attention in predictions. We want to explain to debug. We want to tackle hallucinations and better understand when LLMs hallucinate and what can we do about it. And we are also interested in going beyond simple attribution and more towards interactive XAI. And with the tools which we have, we can exactly do this. We can down-regulate certain neurons, up-regulate other neurons. So if we understand what they are doing, what they are representing, what kind of concepts, then we can do this kind of analysis.